we are hosting Professor Yu, who is the convener of WG4, to give us a presentation on WG4 activities, which is also known MPEG video working group. Let me share a brief background on her. Our speaker is a distinguished professor at the College of Information Science and Electronic Engineering at Zhejiang University. His field of interest covers subjects related to 2D and 3D data compression, representation, and as well as human visual perception and quality assessment for visual content. She has been active in the area of standardization and has contributed significantly to the technical development of standard, as well as leading standardization activities in different forums, from IEEE to ISO IEC and ITUT. She's here in her role as the convener of WG4, which is the working group for MPEG, who oversee technologies and standards related to video compression or video in general, and that covers a lot of new activities that so far she has overseen to come to fruition, like the one for low complexity video coding or the ECM. And now she is kind of leading the way for some of the new projects, like dense light field video coding, as well as video coding for machines, among many other things, not to forget mentioning about the neural network compression and representation as well. So with that brief description, I give you the floor, Professor Yu, to tell us what's happening inside WG4. Thank you.
Thank you very much. Actually, let me switch on my screen. I hope you see my screen.
Yeah, yes, we do.
So if I now my slides in the full screen, I hope.
Yes, yes, it is.
So thank you very much for your invitation. Actually, I'm very glad to have this chance to communicate with you, to share information with you about standardization activities in SC29 WG4 MPEG video coding. Thank you for the introduction. I'm the convener of WG4. And I think many of your members may be already quite familiar with this working group, even though the working group is a young working group. But actually, MPEG video is a long history to develop coding and compression of digital representations of moving pictures, and also working on the coding and compression of descriptions of moving pictures. So I would like to provide a very brief introduction of the most recent activities in WG4, especially for these let's say 5 standardization projects: essential video coding, low complexity enhancement video coding, MPEG immersive video coding, neural network compression, and the most latest one is the video coding for machines. And I will also mention the exploration experiment stage activities of Lenslet video coding, as well as the implicit neural representation of video. So these are the activities recently in WG4. So for essential video coding, actually, the functionality is quite similar as our traditional video coding standards such as AVC, HVC, and VBC, but there is one most important difference is the loyalty related things. So the design of this coding standard is expected to, let's say, announce friendly licensing terms in a good, reasonable period after the standard published. So actually, the standard was formally published in 2002, and there are two profiles defined in this standard. The first one is the baseline profile. Try to use technologies without, let's say, with no loyalty fees, loyalty free. The other one try to include more advanced technologies. That's the main profile. And this standard was published in 2 years before, and the most recent topics related to essential video coding is try to extend it with SEI messages to support green metadata. So that's essential video coding. The second one is the low complexity enhancement video coding, which is the layered design of video coding. The interesting thing of this standard is it can work together with all well-known traditional one-layered video coding standards such as AVC, HVC, VBC, and also EVC. So the defined procedure of this standard is the enhancement layer, but not the basic layer, base layer. So with the enhancement layer, it can provide enhancements for different resolutions, for different, let's say, for different bit rates. And the most recent topic related with this standard is to consider to define a new level to support 8K high frame rate. Actually, this standard is already supported in TV, digital television 3 standard in Brazil. So that's LCVC. These two standards are mostly for traditional video coding. The third standard is the compression of neural networks. Actually, this I believe this will be a very useful standard for especially in the age of artificial intelligence. So more working groups in SC 29, there are activities try to using neural networks for media processing, for media compression, include the JPEG AI, AI-based coding of point clouds and so on. So the first edition of the neural network compression was just published in this August, and actually this standard is a toolbox with different coding tools for neural compression, such as sparsification, pruning, and of course quantization, and a special designed arithmetic encoder for neural networks. And the working group is now working on the second edition, which try to include the incremental updates of any neural networks. So that's what we are working on in the most recent meeting cycles, and the DIS was just issued in this July. So the next topic is the MPEG immersive video. I believe this might also be related with your interest about the dense light field. So, but MPEG immersive video try to compress the multiple view video content to describe the 3D scenes. It may include texture only multiple views, or texture plus depth multiple views. The main challenge for the application is the higher pixel rate, as well as a higher bit rate, because the large number of views. And another limitation we are asked to consider about is we'd better to reuse the existing 2D video codec to support such 3D thing content compression. So in the design of immersive video coding in the MIF encoder and decoder, actually we pipeline the system into the pre-processing of those multiple views, try to organize the textures and depth informations into, we call that atlases. And those atlases can be compressed with existing video codecs, such as HEVC codecs. And additional to that, we also need more information to describe the information in the new generated atlases. So by using such a framework, we can achieve here I provide some numbers in this size as an example. So the input data rate could be dozens of gigabits per second. After this processing, the pixel rate can be reduced to no more than 1 8K video, and the bit rate could be in the range of dozens or no more than 100 megabits per second. And so for the details of the procedure of the encoding is we use the view projection to try to find out which are the redundancy between the different views, and find out those let's say occluded areas in the let's say the basic view, but not in the additional view. So only those occluded areas of the additional views will be included in the packed atlases. So As I just mentioned, the metadata actually are used to define those packing information. So which patch in the atlas is come from which view, from which position, and the camera parameters of each views, and so on. So the packed atlases, actually it's a dynamic video, so you can compress the atlases sequence with existing video codec for both the texture as well as the depth information. And the multiplexed video bitstream as well as the metadata bitstream give us the bitstream of MIF. Actually, this pipeline is quite similar as point cloud compression. I mean the video-based point cloud compression. So we share the same framework and the same framework for the syntax. So that's the video-based volumetric video visual media coding, the V3C. So MIF actually is based on the V3C, but in order to decode the MIF V3C bitstream, we still needed to have our own standard to describe how to reproject the patches in the atlases, in the decoded atlases, to the source views, and so that those source views can be used to synthesize to any virtual view you want to watch for the 3D scene. So that's MIF. And the FDI, we already reached the FDIS for the first edition in October, and from several meetings ago, we already started our work on the second edition. In the second edition, there are more functionalities as well as some new features, such as we can have more flexible camera settings. Those camera settings can also be dynamic, and we are trying our best to well handle surfaces exhibiting non-Lambiscian characteristics, such as in these two sequences, there's a mirror, and there are the glasses and so on. So we hope we can have a better support on such kind of thing. And we also try to support the combination of heterogeneous content, such as video-based multi-views and point clouds in a single V3C bitstream, or even in a single atlas. So that's new functionalities we are working on in the second edition of MIF. So next topic is not yet a real standardization project yet. We start up the topic on the implicit neural video representation, INVR, from July meeting in this year. But I believe this is a very interesting topic. So it's different from the traditional video representation. We usually use 2D metrics to with uniform sampled pixels, but represent the 3D scene or 2D video with the neural networks. So the 3D scene or the 2D video will be represented by a neural network. So if we can compress such a neural network, then we get the compression representation of the thing. So currently, we defined two categories of exploration experiments. One is on the 2D content. So we will try to evaluate the complexity and the coding efficiency of INVR methods on the 2D image or video. So there are activities in WG1 try to use neural networks as a coding a compression tool to compress to the image. But here, the neural network is not only used for compression, the sampled pixels, but used to represent the samples. And people try to find out by using such a neural network, actually the network might be not so complicated as those we used for image compression. So we would like to find out if the complexity could be lower than the used neural network for compression only. So this could be a very interesting thing. The other experiment is on the 3D thing. So we will evaluate the quality and the let's say the temporal consistency of INVR if we use the INVR as a view synthesis method. So this could be a first step on the study on the 3D thing representation. And in the future time, maybe next step, we will pay more attention on the compression efficiency and so on. So that's the a new activity. It might be somehow related with MIF or related with neural network compression. So if you are interested about this topic, you are welcome to join us with this interesting direction. Here is a preliminary experimental results. Actually, this video is generated from a neural network represent this 3D thing. So it's different from those videos I usually show in my report in MPEG. Those are, so in MIF, we use the traditional depth image-based rendering, but here we use the network to represent the content. So the next topic, I believe maybe you are most interested about this topic. So the Lenslet video coding for dense light field. So actually, let's first talk about the Lenslet video coding, Lenslet video. So it's a generalized representation of a dense light field. Lenslet video might be captured between different kinds of cameras. For example, here, the first part of this slide is the content captured by Planoptic 1 cameras, and the middle part is content captured by Planoptic 2 cameras. These two kinds of cameras, in both of these two kinds of cameras, there are micro lens arrays between the sensor and the main lens, but the settings of the micro lens could be different, so that the micro image could be quite different. So in order to convert such content to, let's say, multiple view images, the conversion could be different. And we need different parameters to describe those different content. But we can also use camera arrays to capture dense light fields content. So not only the planoptic cameras can be used, but also camera arrays can be used to capture content of dense light fields. So actually, speaking of the requirements, I think maybe you are quite interested about the requirements of the Lenslet video codings for dense light field. There were multiple meetings. We discussed about the use cases and technical requirements for a potential standard together with WG2. So the latest version is N249 from WG2, a draft use cases and the requirements of such an activity. So in that document, the use cases are categorized into two categories. One is the storage and the other one is communication. So let's talk about these two one by one. So for the storage applications, it mostly relates with cameras and also relates with displays. So here are more explanation and provide more evidences about the content provider, the cameras of different types. So as I just mentioned, planoptic cameras are the major, let's say major device to be used to generate lenslet content. There are micro lenses between the main lens and the sensor. So that's architecture of the camera makes the special structure of the lenslet image, lenslet video. And for those these kinds of cameras, the lenslet image may suffer from, let's say, unknown translations and rotations between those micro lenses. So it is very important to estimate those parameters to understand those sub-picture architectures in the lenslet content. That will be very useful if we want to compress lenslet video content. So as for the compression, we usually need to find out correlations in the lenslet video. There are, of course, temporal correlations between multiple frames of the in the time domain. But in the spatial, the most special thing is the spatial correlation. It might be somewhat different from traditional video. There are spatial correlations, but in that lenslet image, there are angular correlations So not only the nearby pixels exist correlations, but also some special structure or some kind of different distance pixels, distant pixels might exist in correlations. For Planoptic 1 captured camera captured content or Planoptic 2 camera captured content, the spatial or angular or micro image correlation could be different. So that means that when we design the coding tools, we need to consider the structure, the spatial structure, especially the spatial structure in the lenslet image. So I believe this is the most important thing we need to consider for the lenslet video coding. I mentioned the Planoptic camera. Additional to that, there are some special cameras like live field microscopic, which might be used in scientific researches, and those microscopic can capture 3D things like large-scale biological neuron activities with lenslet video. So for those devices, we need to support the compression of large amounts of content. Since there are lenslet arrays, actually the sensor usually have a large amount of large volume of data than usual 2D video cameras. So that's why for such kind of devices, the compression, even you just need to store the data locally, you need advanced coding technologies for those large amounts of data. So that's live field microscopy, and there are also live field endoscopy, which might be used for medicine applications. So the camera with lenslet arrays can be mounted on a bendable cable and to capture the inner 3D scene of a human body, for example. And for such applications, the storage of large amounts of content is also a technical challenge. So additional to that, in the most recent WG2 and 4 meeting, some information about the application of integrated camera arrays be brought to the meeting, and those camera arrays are used for video surveillance, and was provided. The information was provided that some airports, for example, in some of our Chinese airports, set up systems with integrated camera arrays to capture content for video surveillance. Those camera arrays can provide a larger field of view and a larger depth of field. the police can see through occlusions with the assistance of synthetic imaging. And this is a real application. So we believe with such content capture devices, different kinds of capture devices, it is reasonable to establish some standard activities for those special contents. And on the other hand, maybe you will ask, other than the content acquisition devices, we may also need display devices. So here are some analysis about the 3D displays for Lenslet content. So first kind of such display is the integral 3D display. It's a so the Lenslet array again is used here in such kind of display, and such display can provide the viewer the feeling of 3D dimensional perception as well as 2D motion parallax without wear any glasses. So this is the I think we had one workshop in MPEG in maybe 2018 or 19. NHK demonstrates the such a display in the meeting site on the meeting site. And additional to the integral 3D display, there are also layered 3D display. The structure of the display might be different, somewhat different from the previous type. So there are multiple layer architectures in the display, and the light field of 3D can be recreated by the layered architecture of the display. And again, the 3D, three-dimensional perception and 2D motion parallax can be provided without glass wearing. And additional to that, we have also holographic displays, which can regenerate the light field, 3D light field by computer generated holograms. And so such kind of device displays can avoid the convergence and accommodation conflict for the viewers. So it's more comfortable than the traditional 3D displays. So these kinds of displays need to feed in the Lenslet data. Lenslet data have the advantages for more natural, more fluent of bandwidth compared to other 3D data types. So considering of such content acquisition devices and display devices, as well as the application in the medical image, we collect the requirements for these different applications. So we need to support different types of representations of dense light fields. So I mentioned there are different types of Lenslet images and videos. And we also need to support different bit depths, color formats. We are not only need to support high efficiency lossy compression of Lenslet video, but also in some applications, lossless compression might be necessary, might be needed. And additional to the compression of the video data, we also need to transmit information about the architecture of the lenslets and lenses arrays. So metadata need to be considered in the design of such a standard. And we hope that such a new activity can be based on existing video coding standard such as HEVC or VVC. So extending of existing standard could be considered. So that's for the mostly for the storage. For the communication, the most related application could be industry, inspections. I don't think I need to provide more, describe more about this. And there are robotics, especially when we consider the, for example, remote operation, then we need communications of the captured video with Lenslet contents, so that we need to define a standard for communication. So the most important things like complexity, real-time encoding, decoding is an additional requirements for the communication. And that's the application. So then let's take a look at the coding tools we try to collect in several years of preparation for the real standard projects. So we conducted multiple rounds of exploration experiments to those coding tools. So some coding tools are for PlanOptic 1, some are for PlanOptic 2, some may be useful for both of different kinds of content. And this table provides us information about how good those tools, how many coding improvements, coding efficiency improvement can be brought by those different tools. So the tools such as image reshaping to process those Lenslet content with sub images and micropixel based intro prediction, as I just mentioned, the special spatial structure in the Lenslet image. And there are micro lens based search and some special zooming compensated method. And so these are different tools. And recently, the group also tried to combine some of those tools, which may bring us more than 30% coding gain compared to HVC. And actually, we also conducted some experiments based on VVC. So some for different types of content in different coding configurations or intro or random access and so on. But at this moment, I think the coding gain is still not so many if we consider the actually the screen content coding. It might be useful for Lenslet video coding, but the those new coding tools bring us some percentage of coding gains, but it seems still not so sufficient to really start up a new project at this moment. So we are welcome to collect more evidences on new coding tools to see if we can ready to start up a real standardization activity on Lenslet video coding. Okay, so I need to move faster. So next topic is video coding for machines. This topic was raised actually more than 3 years ago. The use cases, I believe it's clear. Now more and more video are consumed by not only by human being, but also intelligent machine in the applications like surveillance, intelligence, transportations, smart cities, intelligent industries, and so on. So in 2019, the new adult group was established in requirement group. And after several years study on this topic, in this April, a formal call for proposal was issued, and that was for the track 2. I will explain what's the difference between track 1 and track 2. And in the most recent WG MPEG meeting, let's say, the responses were received, and the standardization activity was moved from the requirement to the technical group, which is WG4. So actually, let me explain about the track 1 and the track 2. At the very beginning, we believe since the video will be consumed by intelligent machine for some, let's say, different tasks. So we believe the features used for those tasks might be more, if we compress the features instead of the original videos, might be more efficient. But things this will change the pipeline quite a lot. So it's really not so easy to define clearly what the feature is. How can we define the feature? If the features are decoded, how can these features be consumed by intelligent machines for tasks? So we find out this might need more time to well understand the pipeline, the technologies. So that's why we actually define the second track, which is more similar pipeline like a traditional pipeline of video coding. The only difference is that after the decoding of the reconstructed video will be faded into a intelligent machine. So for the encoding and decoding, the feed in is the video and the feed out is also a video. So this makes the pipeline more clear. So we decided to start of the activity from track 2 instead of track 1. In October meeting, we received 17 responses from 16 organizations, and this table in the report of the CFP responses provide us the coding efficiency, coding gains from those responses. The most efficient results are listed in this table. From this table, we can see there are different tasks such as object detection, instance segmentation, and trackings. And we have multiple data sets to test those coding efficiencies. And if you want to know a little bit more about techniques, I think this is a good diagram to collect. I try to collect all the tools appeared in those responses. So in the VCM encoder, there are pre-analysis to mimic the analysis maybe happened after the decoding. And with the analysis, there might be different kinds of processing, like spatial or temporal downsampling, or even region-based downsampling. And some tools even remove the background or blurring the background or lower down the refreshment of the background and so on. And after that is the inner encoder. In some responses, they just use the existing encoder, VBC or EBC. And in some responses, they provide us some new design of the inner encoder, like neural network-based encoder or layered-based layered encoder. And in the decoder side, after the inner decoding, we need to restore the images, videos, for upsampling, for background filling, and so on. So then the decoded video will be fed into the same network. So that's the very brief idea about the VCM technologies. So we are not sure which one is better than the others. So we decided to establish a common reference software based on the responses. And the first version of the common reference software will be available very soon in December. And with this framework of software, we can conduct 5 core experiments on the ROI-based coding methods, neural network-based coding, frame level, spatial resampling, temporal resampling, and post-filtering, and so on. So we hope in next meeting, we will have more information about the efficiency of those tools, which may define the first working group draft. So I think that's the things I would like to share with you. The last slides, I provide the information about our communication methods in WG4. So we have a mailing list for the working group and for different ad hoc groups. Okay, that's my presentation.
Thank you so much, Professor Yu.